So the second common feature of the forces is that just as mass determines how gravity affects a particle and electric charge determines how the electromagnetic force affects it, particles are endowed with certain amounts of strong charge and weak charge that determine how they're affected by the strong and weak forces. These properties are detailed in the table in the endnotes to this chapter. Okay, let's see, where are the endnotes? Okay, we'll see later. But as with particle masses, beyond the fact that experimental physicists have carefully measured these properties, no one has any explanation of why our universe is composed of these particular particles with these particular masses and force charges. So that's the thing. We don't really understand the why of these particles. We sort of know them, we've seen them, we've observed them. We did experiments that created them, or experiments where we observed them for the first time and we discovered them, and Nobel Prizes were given for these discoveries. Good, all good. But we don't have an overarching theory that explains why these particles are even a thing. The deeper insight about them is still sort of missing, is the point of this author. Hi, Peter. Peter says, I've been here for a bit listening. Oh, good. Hello, Peter. Notwithstanding their common features, an examination of the fundamental forces themselves serves only to compound the questions. Why, for instance, are there 4 fundamental forces? Why 4? Why not more? Why not 5 or 3 or perhaps only 1? Why do the forces have such different properties? Why are the strong and weak forces confined to operate on microscopic scales while gravity and the electromagnetic force have an unlimited range of influence? So that is something common between electromagnetism and gravitation, is that they're very long range. Now, of course, gravitation is weaker than the electromagnetic force, but still very long range. Another thing about gravitation is that it's always only attractive, whereas electromagnetic force has both attractive and repulsive nature, depending on opposite charges or like charges. So, some similarities and some differences even between those two forces that are usually well understood, but still, it's still a bit of a mystery why there are these forces, to appreciate, and why do the forces have such different properties? Why are the strong and weak forces confined to operate on microscopic scales while gravity and the electromagnetic force have an unlimited range of influence? And why is there such an enormous spread in the intrinsic strength of these forces? To appreciate this last question, imagine holding an electron in your left hand and another electron in your right hand, and bringing these two identical electrically charged particles close together. Their mutual gravitational attraction will favor their getting closer, while their electromagnetic repulsion will try to drive them apart. Which is stronger? There is no contest. We already know. By the way, do you know which is stronger? Have you been paying attention? We already know who's going to win. The electromagnetic repulsion is about a billion. So 10 to the 42 times stronger. If your right bicep represents the strength of the gravitational force, then your left bicep would have to extend beyond the edge of the known universe to represent the strength of the electromagnetic force. Wow. Quite a workout there. The only reason the electromagnetic force does not completely overwhelm gravity in the world around us is that most things are composed of an equal amount of positive and negative electric charges whose forces cancel each other out. On the other hand, since gravity is always attractive, there are no analogous cancellations. More stuff means greater gravitational force. But fundamentally speaking, gravity is an extremely feeble force. This fact accounts for the difficulty in experimentally confirming the existence of the graviton. Searching for the smallest bundle of the feeblest force is quite a challenge.